Hi everyone, I'm Neeta Goel, CEO at Newt Global.
And hi everyone, I'm Sandeep Rajiv. I'm the sales director at Newt Global.
Today we will be talking about migration considerations to go from Oracle to Postgres. If you are considering migration from Oracle to Postgres, this talk is for you. My team has been focused on building platform for assessing the complexity of databases and underlying schema, making it compatible to Postgres through auto remediation. In today's session, we'll cover systematic approach with some examples to get to Postgres faster, smarter, better.
Thanks, Neeta. To introduce myself, I have over a decade of experience in technology sales and specialize in helping organizations successfully navigate complex database migrations, particularly from Oracle to Postgres. I work closely with stakeholders to align migration strategies with business goals, ensuring that transitions not only reduce costs but also drive long term value. Today, we will be discussing important considerations when migrating from Oracle to Postgres and the tools and framework to accelerate and streamline this transformation journey. When modernizing from Oracle to Postgres, it's critical to address several key considerations right at the outset. Every layer of the technology stack must be evaluated, from database schemas and applications interfacing with the database to upstream and downstream interfaces, batch jobs, shell scripts, infrastructure, and testing. In the following sections, we will explore each of these areas in detail. Oracle is a robust database and offers large number of features. Many of these features are not yet supported in Postgres, leading to the complexity in migration while keeping the same functionality and performance. One of the most complex and labor intensive steps in any Oracle to Postgres migration is schema conversion and remediation. And a big question we often hear is, how do I convert my PL/SQL? Stored procedures, functions, and triggers often contain embedded business logic that needs to be translated to Postgres compliant constructs. We will be discussing some examples to give you an idea of what needs to be addressed for schema to work in Postgres correctly.
In Oracle, simple addition works even if variable is null. The result becomes null and that's accepted. However, in Postgres, if you try to assign null plus 1 to a numeric variable, it can cause error. So we wrap it with coalesce to safely treat null as 0. This ensures consistent behavior and avoids null issues at runtime. Similarly, in handling null versus a string, empty string, in Oracle, empty strings are treated the same as null. So checking if PV doc code is not null automatically excludes both. But in PostgreSQL, empty strings and null are distinct. So to match Oracle's behavior, we need to use nullif to convert empty string to null. This ensures the condition will work if null or empty string exists, just like in Oracle. It's a small but important adjustment to ensure functionality of the code works as intended. Continuing, we need to consider date operations. There are many variations: date without timestamp, with timestamp, without time zone, etc. Here is an example of trunc operator and typecasting required to deal with different variations of date format. In Oracle, trunc works for both date and numeric values and handles it implicitly. In PostgreSQL, date trunc and trunc have distinct purpose and they are used for date and numeric values respectively. Additionally, if variable value date is a date without time component, typecasting is explicitly required. Moving on, there are special features in Oracle which don't have a direct equivalent in Postgres. Identifying such features used in a schema being converted is a prerequisite. It's a long list of features. Some commonly occurring cases are package global variables, associative arrays, dynamic sequels, for all, goto, etc. Each of these objects require a specific treatment to ensure equivalent functionality in Postgres. Here is one illustration for a complex schema with about 200,000 lines of PL/SQL code. Identifying every occurrence of these special features is possible only by automating scanning and remediation of PL/SQL code. Many tools comment some features, and many features are ignored and not identified in compilation, resulting in runtime errors. Take an example of package global variable that persists throughout a session. In one single schema, we had over 700 of these variables. PGV can be handled using GTT approach, but requires identifying each incident of PGV used inside the PL/SQL and specifically using set every time. Another example is goto, which is a programming construct and identifiable only if a line-by-line code scan is done. If goto is commented, PostgreSQL objects will compile and will result into unintended program runtime errors. Dynamic SQL is another example. There is no compilation error if it is not converted, and identifying dynamic queries is critical for ensuring code compatibility with PostgreSQL. PostgreSQL handles dynamic SQL string directly using concatenation, and there are many nuances while making the changes in the syntax. Replacing execute immediate with execute, changing position variables, and introducing concatenation, etc. As you saw in the previous example, having to find over 1600 execute statements manually would be almost impossible and will introduce significant human error if remediated manually. Next important consideration is differences in data types in Oracle versus PostgreSQL and how implicitly Oracle handles these data types and values contained within. In Oracle, the database engine is more flexible with implicit data type conversions. If you're using a string or integer in a numeric expression, Oracle often automatically converts it to the appropriate type. However, in Postgres, the type system is stricter and more explicit and requires data type to be specific. Differences are subtle and mostly not identifiable in compilation. These issues mostly manifest as runtime errors or inconsistent results. Here is an example of a schema with number of table columns. If these columns are referred to in PL/SQL, typecasting is required in thousands of places to ensure consistent treatment. In another example here, EPS underscore QS can be a text or varchar column in Oracle, and as long as it contains numeric value, Oracle interprets it implicitly and expression is valid. However, same will fail in PostgreSQL unless EPB underscore QS is typecasted explicitly as numeric. The list continues. Date handling is also very sensitive in PostgreSQL and requires explicit instruction for operation and syntax. Oracle PL/SQL has implicit handling of dates in arithmetic operations. When you add a number to a date or timestamp data type, Oracle implicitly treats that number as a number of days. So term date plus 1 directly adds 1 day to the term date. However, PostgreSQL is more explicit about date and time arithmetic operations. Adding an integer to a date or timestamp column directly is not implicitly treated as dates. Instead, you need to explicitly specify the interval you want to add using interval keyword. Continuing in Oracle, toDate supports both date and time implicitly. The date variable here is having timestamp without time zone. In Postgres, toDate only handles dates. For date with time, conversion to timestamp is needed. Default return value from to timestamp is with time zone. Firstly, to understand variable data type requires complex logic for lineage. In this case, first finding that a date is having timestamp without time zone is needed, to then automatically typecasting it to match date variable a date. Automating these conversions helps eliminate manual guesswork, reduce risk, and speed up what is traditionally the most challenging part of migration.
Next, we will look at things to consider for understanding the Oracle database performance metrics to determine the right target configuration on Postgres. We need to understand key workload characteristics like CPU usage, throughput, IOPS, and storage patterns. Additionally, data distribution plays a major role. This includes analyzing partitions and subpartition counts, their sizes and types, whether it's range, list, or hash. Doing all of this manually by reviewing AWR trends, server parameters, and schema details is very time consuming. Automating this step helps accelerate the process and ensures we choose the right architecture and sizing in PostgreSQL, reducing both risk and rework. Now we will discuss the various aspects we need to consider for a successful data migration. The data migration journey begins with a pre-migration phase where the strategy is defined, validation criteria established, and the environment is prepared, including a review and update of key server parameters. In the planning phase, the source system is analyzed in detail to determine the appropriate migration treatment for each object, whether it's a full load, incremental load, or transformation heavy. Tables are then grouped and sequenced based on dependencies to ensure orderly execution and minimal downtime. During migration execution, the process includes automated setup of the target PostgreSQL environment and continuous monitoring of the performance and errors. The ability to rerun failed or partial migrations incrementally, avoiding full restarts, significantly reduces the time needed to do the full migration. Finally, post migration validation ensures both physical and logical accuracy, confirming data consistency, format integrity, and successful conversion from Oracle to Postgres. Now, let's talk about a critical and sometimes overlooked part of the database migration, the application side. Because no one migrates a database in isolation, the applications built around the database have to come along for the ride. We will walk you through some of these real world cases using code snippets from both Oracle and Postgres to highlight the key differences and demonstrate the necessary changes.
One of the biggest challenges in embedded SQL remediation applications, especially legacy ones, often have hard coded Oracle SQL, both static and dynamic. These queries are written with Oracle specific syntax and data types that PostgreSQL simply doesn't recognize. We need to systematically identify and update these, and that alone can be a massive effort. In this example, scanning the source code led to discovery of session.create SQL query, where Oracle specific pattern, sysdate, and the use of from dwell is flagged. Using rule based logic, these constructs are auto converted to be PostgreSQL compliant, replacing sysdate with the statement underscore timestamp and removing from dwell, which isn't needed in PostgreSQL. Dynamic SQL often presents even a bigger challenge than static queries because it is built at runtime using string concatenation. In this case, application code needs to be passed to recognize dynamic SQL.append statements and detect Oracle specific syntax. In this case, trunk sysdate embedded within the string literal. Using role-based engine, these constructs are auto-converted to PostgreSQL equivalent, replacing trunk sysdate with date trunk day statement timestamp. Then there are data type changes that needs consideration. PostgreSQL may require different representations. For example, Oracle's number might need to be mapped to numeric, integer, or even big int, depending on the context of the variable. These changes ripple through the application code, especially in type languages such as Java or .NET, where strict type handling can lead to runtime errors if not handled properly. Changes in application corresponds to changes in the data types in PostgreSQL converted schema. To ensure type safety, auto conversion of code using rules, replacing getString with getInt for those specific fields. This avoids any potential runtime mismatch errors, which are common when database type changes, but application logic is left behind. These data type changes are extensive and are one of the major causes of conversion projects failing as the changes are found during functional testing. Procedure and functions is another consideration used within application. These needs to be reviewed and modified. Applications that rely on calling Oracle stored procedures, especially those using PL SQL specific construct, such as out parameters, exceptions, often need to be restructured. Postgres procedural language, PSQL has different conversions and functions behave differently in terms of transaction scope and error handling. In the example here, Oracle uses call word for all cases, be it stored procedure, function, packages. However, at the time of transformation, packages are converted to stored procedures or functions. In this example, we have replaced select keyword for Postgres compatibility for calling a function. We need to also consider input-output parameters used within procedures and functions. Oracle variables within procedure functions needs to be replaced with equivalent Postgres, SQL, Java methods in line with data type changes on DB side. And let's not forget interfaces, shell scripts, jobs. The list goes on. Embedded SQL is everywhere. There are batch of shell scripts and interfaces which usually have Oracle specific syntax. Every interface needs to be assessed for any Oracle specific syntax, and remediation is needed. Here, SQL Plus is an Oracle construct to execute a SQL command from within a shell script. There are many aspects to take care to make this code snippet compatible to PGSQL, starting with replacing SQL plus keyword with pSQL, then handling attributes for functionality to avoid printing header and footer in result set. Alter session needs to be replaced with search path. In this example, alias is used in set statement, which is not supported in pSQL and needs to be removed. As you can see, there are many syntactical changes required. In a complex batch heavy database, there will be hundreds of such SQL plus statements needing remediation. As you can see, there are changes in syntax, data types, unsupported features everywhere, from schema, batch job, interfaces, application, you name it. The only way to succeed is by automating all the things.
And this is where DMAP comes in. DMAP is an AI integrated platform designed to accelerate Oracle modernization to Postgres. It streamlines the entire migration process from both the database and application perspectives. On the database side, it starts with a comprehensive discovery and assessment phase, analyzing schema complexity and database performance to recommend the ideal PostgreSQL configuration. It can generate a business case with TCO comparisons to help clearly see the cost benefits of migration. Once the assessment is done, DMAP shifts to automated migration, handling everything from schema conversion, including complex objects like stored procedures and functions, to data migration and validation. This significantly reduces manual effort and migration risks. On the application side, DMAP scans the codebase to identify embedded SQL, both static and dynamic, and calculates the conversion effort needed to make it PostgreSQL compliant. It even automates handling of data type changes that might affect application logic, making the transition smoother and more reliable. However, automation alone will be like chaos with no plan. To succeed in migration, you need a framework that brings structure, strategy, and the full power of automation together. This is where the CMC framework comes in. It surrounds DMAP's AI driven automation with everything needed for a successful migration. In addition to the automation, the framework supports infrastructure setup and robust testing across environments to catch issues early. Finally, it enables a planned, low risk production cutover, ensuring a smooth go live. This would help deliver the migrations 4 times faster. A typical medium sized database migration that would have taken 12 months can now be delivered in 12 weeks. Now, you have a full understanding of the configurations, tooling, and framework to undertake your journey to cloud native PostgreSQL on Azure. Are you ready to onboard? Thank you.